Hello, everyone.
This is Phang with my partner Elijah Courtney, and today we will be presenting our project in which we observe the diffusion of food dye by Brownian motion in three fluid media. Brownian motion is a theory that describes the random motion of small particles through fluids under the condition that they have roughly equivalent densities. From a historical standpoint, the botanist Robert Brown was the first to notice the unsystematic movement of these particles by observing pollen grains in water using an early microscope. In 1905, Albert Einstein showed that random forces causing the particles to move was due to thermal excitations of molecules in the fluid medium. 3 years later, Paul Langevin derived stochastic equations of motion for a Brownian particle, verifying Einstein's result. These are called the Langevin equations and are shown as equations 1 and 2. They are actually based on Newton's equations of motion, although they have been modified to show that friction forces of the form negative gamma v of t dominate the movement. A stochastic force xi of t has also been added to account for random density fluctuations in the liquid. The prediction of the modern theory of Brownian motion is the diffusion coefficient given in equation 3. In this equation, k sub b is the Boltzmann constant, T is the temperature, eta is the dynamic viscosity, and r is the radius of the particle. Because Brownian motion is random, it cannot be measured deterministically. Instead, we apply statistical principles by calculating mean squared displacements of Brownian particles using the formula given in equation 4, which describes the mean squared displacement of n moving particles at a time t. R is the position of the ith particle. The mean squared displacement can be related to the diffusion coefficient by equation 5, and we will later use this result to develop a model for data fitting. To observe Brownian motion experimentally, we used Brilliant Blue FCF dye as the Brownian particles and water, acetone, and 91% isopropyl alcohol in water as our fluid media.
The initial aim of the experiment was to track the motion of individual Brownian particles suspended in different fluids using the method and design shown. To this end, we collected a variety of different particles, including 6-micron colloidal particles borrowed from Dr. Yiping Zhao. We then constructed a microscope by aligning inexpensive laser pointer collimator lenses in front of a smartphone camera, inspired by a design used by a previous group to study red blood cells. However, due to the poor quality and physical design of the purchased lenses, we were only able to achieve approximately 40 times magnification, and the resulting quality of the videos was deemed insufficient to resolve the Brownian motion of all particles tried. This is a looped video taken of aluminum particles in water, using the lens and smartphone system shown in the last slide and played at 4 times speed. As you can see, many particles have clumped, sunk to the bottom, or floated to the top. However, certain smaller particles, estimated to be approximately 20 microns in diameter from calibrated pixel measurements, can be seen moving and glittering to the middle and right side of the frame. However, because each is only 1 or 2 pixels large, the apparent size is too small to obtain meaningful data.
Figure 1 shows our final experimental design. In this setup, a ceramic dish was filled with 1 centimeter of the fluid medium. An adjustable stand was used to hold the smartphone over the dish for observation purposes. 2 incandescent lamps provided a constant lighting source for the setup. Approximately 0.5 milliliters of dye was dropped into the fluid. The smartphone was used to record videos of the diffusion at 30 frames per second with a 1920 by 1080 pixel resolution. Since the diffusion constant is dependent on temperature, we performed the experiments at a roughly constant temperature of 290.5 degrees Kelvin, measured by a digital laboratory probe so that the data could be comparable. Shown here is a comparison of our experimental setups in theory and in practice. We took several measures to reduce the effect of external factors on the experiment. As you can see in the figure on the right, the ceramic dish, which was chosen for a smooth surface, was placed on a concrete floor to minimize vibrations. We also used a digital level and paper shims to measure and adjust the dish so that it was within a tenth of a degree to being perfectly horizontal. When the fluid media was added to the dish, it was allowed to sit for a while so that it could settle and reduce initial current. Finally, we dropped the dye from within 1 centimeter of the surface of the fluid to minimize the mechanical energy transmitted into the system. Shown on the left are the materials we used in our final setup. Our Brownian particles were the Brilliant Blue FCF food dye. We used water, 91% isopropyl alcohol, and acetone as our 3 fluid media. These materials could be purchased for a total of less than $20. The adjustable stand was constructed for holding the smartphone, and the incandescent lamps were used to provide the lighting for the experiment. Shown on the right are the materials used in the previously described initial setup, which was tried and failed. The laser lenses were purchased for $10. The powdered aluminum was extracted from firecrackers by dissolving the propellant in water and skimming aluminum from the top. Molybdenum disulfide, tungsten disulfide, and boron nitride, which had estimated particle sizes of between 3 and 20 microns, were readily available from past experiments conducted by the Courtney's research consulting group.
This chart shows the logical flow within the Python code written to process the extracted frames from a given video. Because of the absorption of light, the darkness of a pixel is proportional to the number of particles between the camera and the dish in the area represented by that pixel. Based on this premise, performing a weighted average will give the average radius of a particle, i.e., we can obtain the mean radial displacement. The radius r0, calculated as the radius of the initial blot and shown in black in figure 5, is used to exclude the weight of all particles that did not reach their position by diffusion. The plots shown were primarily used to calibrate the video analysis program, but serve as an intuitive double check that the method of weighted averages produces reasonable values of the mean displacement. Now shown is a side-by-side comparison of the diffusing dye in isopropyl alcohol, and the plot generated by digitizing pixel measurements for each frame. The video is played at 8 times speed, and one plot is generated every 10 seconds. The false color in the plot represents relative intensity. The solid black circle in the center of the plot represents the invariant initial radius r0, and the white circle represents the calculated mean radial displacement for each frame. As you can see, diffusion occurs radially outward, indicating a successful elimination of outside compounding variables such as large-scale fluid movement. Once mean radial displacement was calculated, it was converted from pixels to meters using measurements made with a ruler of known length for each video, and plotted as a function of time. The displacement time data was fit to 2 models, as shown in figure 6, and will be discussed later.
To generate a fit model for our experimental data, which we will call fit model 1, a nonlinear least squares fit was performed by modifying the relationship between the mean square displacement and the diffusion coefficient to obtain the model given in equation 7. Here, d is the diffusion coefficient calculated from the dynamic viscosity, Brownian particle radius, and temperature. Notice the addition of the d0 parameter. This is to account for the initial displacement of the food dye. In the trials in which isopropyl alcohol was used as a fluid medium, the dynamic viscosity was fixed using equation 8, as the fluid was not pure isopropyl alcohol. Unfortunately, residual analysis and visual appraisal showed that fit model 1 did not fit well to the experimental data. To address this issue, we use the basic power law shown in equation 9 as a second fit model, which we will call fit model 2. Here, A, B, and C are constants. C is intended to account for the initial displacement of the particle and is analogous to d0 from fit model 1. B is an estimate of how much of the observed motion can be attributed to Brownian motion, with B values other than 0.5 suggesting that other effects are present. Since we use the general power law, not much is known about A except that it is some rate coefficient. A relationship between A and the diffusion coefficient can be found, but knowing the exact relationship between these quantities is inessential to this project.
Now shown are the fits and residuals for all 5 water trials. As you can see, the power law invariably fits better than the adjusted Brownian motion displacement equation, with smaller, more random residuals. As discussed later, we believe this is due to the presence of other interactions overpowering the observable effects of Brownian motion. Because the p-values for both models are close to 1, both models are considered to be good fits to the data. However, for this medium, the sum of squared errors is approximately 2 orders of magnitude smaller for the second model, again indicating that the second model is much better than the first. As discussed later, the fit values of D are many orders of magnitude larger than the expected values for all reasonable particle radii, resulting in a predicted value of R that is much too small. The large standard deviation indicates that some outside source of error was not controlled.
Shown in these figures are the plots of mean displacement versus time for the trials in which isopropyl alcohol was used as a fluid medium. The experimental data is plotted as green points, while fit model 1 is represented by the green line and fit model 2 is shown as a red line. These plots follow similar trends as the trials with water, except some of these graphs, for instance trials 2, 3, and 4, are shown to be even more linear than the graphs for the water trials. The residual plot corresponding to fit model 1 display a distinct pattern. On the other hand, the residual plot corresponding to fit model 2, plotted in green points, does not follow an apparent pattern. Along with the fact that the sum of squared error for fit model 2 is smaller than the sum of squared error for fit model 1, these plots show that fit model 2 is indeed a better fit to the data. Shown in table 2 are the results of chi-squared analysis and the predicted parameter values for both fit models. The p-values for both models show that the fit models are not statistically different from the experimental data. There is a larger discrepancy in the p-values and a smaller discrepancy in the sum of squared error between the two models as compared to the water trials. However, the diffusion constant predicted by fit model 1 is still many orders of magnitude larger than expected values, and as a result, the radii of the particles predicted by fit model 1 are orders of magnitude smaller than expected. Additionally, large standard deviations indicate that there are some external uncontrolled factors. As in the water trials, D0 and C are similar, with only a 14% difference between the two quantities. The B parameter is not equal to 0.5, indicating that effects other than Brownian motion may be contributing to the movement of the particles.
As mentioned previously, the predicted value of particle radius r is much too small. This is immediately known because the predicted radius is 2 orders of magnitude smaller than a single angstrom, the approximate length of one carbon bond. Pictured is the structure of component Brilliant Blue FCF molecules, clearly composed of more than one carbon bond. Because it is unlikely that the suspended particles are truly the component dye molecules, the true particle size is likely even larger. Although the trials with water and isopropanol produced incorrect results, the experiments were able to be conducted. By contrast, the acetone medium produced no usable data. The acetone's mechanical motion appears to last much longer, and it diffuses 8 times as quickly as the isopropanol, initially leaving a relatively empty central region and depositing a sticky residue not present in either other medium. Because of the unusual speed of its diffusion, the increased duration of the initial mechanical motion, and the observation that not all dye remained suspended, acetone was disqualified as a medium.
To verify our suspicion about the inaccuracy of the diffusion coefficients predicted by fit model 1, a simple program was written to calculate a range of diffusion coefficients using a range of particle radii from 30 nanometers to 40 microns as input. This resulted in diffusion coefficients ranging from 4 times 10 to the negative 15th to 4 times 10 to the negative 12 meters squared per second. The fact that the diffusion of dye was clearly more rapid in acetone than in isopropyl, and approximately twice as fast in isopropyl than in water, suggests that the miscibility, solubility, and relative viscosity of water glycol solutions in our 3 fluid media are candidates for sources of error. Furthermore, by considering particles outside the radius R0, we have also assumed that all particles start on the ring of radius R0. As a result, using equation 6, which predicts the mean displacement by performing a weighted average of darkness values, the average will be incorrectly weighted closer to the defined origin. The error that arises from this assumption implies the systematic underestimation of mean displacement, which would lead to a smaller fit value for the diffusion coefficient and hence a larger fit value of particle radius, based on the equation used for fit model 1.
Overall, it's clear that the power law provides a better fit than the derived Brownian motion equation. The derived equation does provide a reasonable fit based on p-value and sum of squared error, but many of the data sets are easily observed to not fit a square root model. In addition, despite any systematic errors inclining the analysis towards slightly smaller values of the best fit parameter d, it is absurdly large when compared to all reasonable values. This difference may be attributable to the miscibility or solubility of the water glycol solution in the fluid media, but can likely be reduced by using lab standard dye powder instead of commercially available food coloring, and creating the initial dye droplet by forming a solution of known concentration with the medium in question. In conclusion, this experiment was unable to utilize diffusion to measure the effect of Brownian motion without the overwhelming influence of other undetermined phenomena.